Morning, everyone. My name is Alberto Salleo. I am a faculty in the Material Science Department at Stanford University, and I'm welcoming you to the Franco Strazzabosco Young Investigator Award of ISNAF. ISNAF is the Italian Scientists and Scholars in North America Foundation. We are the largest not-for-profit organization that regroups scientists and scholars that are located in North America, that is the US, Canada, and Mexico. Our mission is to connect, empower, and celebrate the Italian diaspora located in North America. As part of the celebration, we have our Young Investigator Awards that are extremely competitive, where we reward and celebrate our best researchers in different areas. And this morning, we're here for our symposium to listen to the 3 finalists of the Franco Strazzabosco Award for Research in Engineering with focus on sustainable energy. This award was established in 2013 by the Strazzabosco family in memory of Dottor Ingegner Franco Strazzabosco. It is a tribute to the entrepreneurial courage of Italian engineers who strive to apply scientific discoveries to the public advantage. The way this symposium will work is we have 3 finalists who will give a brief presentation, and then you will be invited to ask questions. Please put questions in the Q&A section that you should see at the bottom of your Zoom bar. Following the presentation, a jury composed by Dr. Pecora, who is a program manager at the Department of Energy, Professor Scovazzi, who's a professor at Duke University, and Professor Stingelin, professor at Georgia Institute of Technology, will decide the winner of our award. I should say right away, I was in the review panel that selected the 3 finalists, that this was an extremely arduous task, as the application pool was very competitive. Nevertheless, we had to find 3 finalists, and I'm very excited to introduce to you our 3 finalists. We have Dr. Matteo Bertagni, who is currently a postdoc in the Civil and Environmental Engineering Department at Princeton University. Dr. Luigi Osmieri, who is a staff scientist at Los Alamos National Laboratory, and Dr. Lorenzo Rosa, who's a staff scientist at the Carnegie Institution for Science. He's also an assistant professor by courtesy at Stanford University. So without further ado, I will leave you with our finalists. The Q&A session will be moderated by Professor Scovazzi, and at the end of our symposium, there will be a few words from the Strazzabosco family. Guglielmo, the floor is yours. You are currently muted.
Sorry. Okay, we can start with the first candidate. So if you could connect, the floor is yours.
Okay, let me share my screen. Okay, can you see the screen?
Yes.
Okay, that's great. Good morning, everyone. Thank you for giving me this possibility. It is really an honor to participate to this award final. Today, I'm going to talk about my research at the Carbon Mitigation Initiative at Princeton University. And my research focuses on hydrogen energy and its potential criticalities, impacts, trade-offs on the Earth system components and on climate. Let me first start by introducing why hydrogen is so important. I think it's safe to say that hydrogen is the most promising fuel for a low carbon future. Hydrogen can be produced in a variety of ways from different energy and feedstock sources. So its production is versatile and scalable. Currently, most of hydrogen is produced from fossil fuels. It's very carbon intensive, but there are ways to lower the carbon footprint of hydrogen production. One is to couple the fossil fuel like steam methane reforming with carbon capture and storage, to obtain the so-called blue hydrogen, or use renewable energy to power the electrolysis of the water molecule to obtain the so-called green hydrogen. Now, once we have obtained hydrogen, it is a fuel that can be used for energy purpose. It releases a good amount of energy on a mass basis. And the very cool thing is that the only byproduct from stoichiometry is water. And that's where hydrogen got its name originally from ancient Greek, meaning water creator. Now, accounting for this potential, there are a lot of plans for large-scale hydrogen production across all continents. This is a map I did starting from the data from the International Energy Agency that shows how Australia, Europe, and US are leading the way, but the hydrogen production plans are widespread across the world. And as an environmental engineer at the Carbon Mitigation Initiative, we clearly want to design effective and safe climate change mitigation solution. And we also want to minimize the potential for risks associated with these strategies and also optimize their adoption. So one of the first questions I had in mind is, what are the consequences of potential hydrogen emissions? What if we lose some of this hydrogen to the atmosphere? And we'll see that hydrogen is actually an indirect greenhouse gas effect because it interacts with other greenhouse gas in the atmosphere, in particular methane, which is the second most important cause of global warming after CO2. We're going to talk about the crucial role of soil bacteria in the global hydrogen cycle and how they basically are mitigating the impact of hydrogen emissions. Then we're going to touch base on the challenges that hydrogen faces for international transport and storage, and how ammonia has emerged as the most viable option for the industry to transport hydrogen from different regions. And I'm going to conclude mentioning the ongoing research about hydrogen production. So to start, I need to share with you what we already know about the hydrogen cycle. Hydrogen is a trace gas in the atmosphere with a concentration of around 0.5 ppm, so 3 orders of magnitude lower than CO2, and an average lifetime of 2 years. There are different sources of hydrogen to the atmosphere, and what I want to mention is that most of the hydrogen is actually produced within the atmosphere itself. And in particular, methane oxidation by the radical OH, which is called the detergent of the atmosphere, leads to hydrogen as byproduct, and so do volatile organic compounds when oxidized. And hydrogen gets removed from the atmosphere mainly by 2 pathways. The most important one is soil uptake by bacteria. This is by far the most important term in the global hydrogen cycle. It accounts for around 70–80% of hydrogen atmospheric removal on a yearly basis. And the second one is the removal within the atmosphere itself. And this is crucial because hydrogen reacts with the same molecule that is responsible for removing methane from the atmosphere. This means that if we emit some hydrogen emission to the atmosphere, there is less availability of OH to react with methane. And so it has been long known that emitting hydrogen to the atmosphere increases methane lifetime. It can also produce tropospheric ozone and produce stratospheric water vapor. And these are all effects that give hydrogen an indirect greenhouse gas effect. And what more recent global climate model tell us is that hydrogen has a global warming potential that is actually pretty big, around 10 on a 100-year time horizon and 35 on a 20-year time horizon. And the global warming potential is how much infrared radiation gets absorbed by the atmosphere as compared to CO2 on a mass basis. And the interesting thing here is that the major feedback is associated with methane, more than 50% of hydrogen indirect greenhouse gas effect. So I really wanted to deal with this problem since there are global efforts to mitigate methane emissions and methane levels in the atmosphere. And it's interesting that hydrogen and methane are not only linked in the atmosphere because they compete for the reaction with the radical OH, but they also linked at the industrial level. Currently, most of hydrogen in the world is obtained from natural gas by steam method reforming. And it's likely that in the next years, and decade, blue hydrogen production will be the dominant hydrogen production method. So we wanted to include all these feedback in a model that could be versatile enough to allow us to develop scenarios. So we develop a box model, which has the mass balances for atmospheric methane, hydrogen, carbon monoxide, because this is the main sink for the radical OH. And we have all the removal terms that have first order closure. We clearly have atmospheric observation of these concentrations. So these are prescribed. So are the sources. We have the removal terms with the OH. Some of these removal terms become sources because, as I said, methane oxidation, for example, produces hydrogen as a byproduct and also carbon monoxide. And then we have methane smaller sink and the hydrogen soil sink, which again is a huge term in the global hydrogen cycle. Now, using this model, we could show that the current atmospheric condition can be represented by a stable node. So any perturbation compared to the current condition decays in time. But the interesting thing here is that the stability analysis shows that the eigenvectors are non-orthogonal. And this means that if we perturb the hydrogen concentration, here, for example, it's an emission pulse of hydrogen, this is associated with a drop in the OH concentration. And this drop in the OH concentrations leads to a progressive build-up of methane as long as the hydrogen perturbation fades away. And then the methane perturbation decays with its own timescale. And so the net effect is that basically we have a long-term impact of methane of a relatively short-lived gas like hydrogen. Since this model reproduces climate model results, or at least the global average atmospheric results, we could use it for different scenarios, and in particular for the purpose of the energy sector. We consider what happens if hydrogen production displaces around 15% of fossil fuel energy. So this would require around 500 megaton of hydrogen per year, which is what the International Energy Agency says we need for reaching net zero at the global scale. Now, here we account for the emission change for methane and for hydrogen. So hydrogen clearly has some emission depending on how much hydrogen we leak into the atmosphere. And this is a very unknown number at the beginning, at the current stage. So we explored a different range of values. And for methane, we consider that if it is green hydrogen, we're clearly going to remove some of the methane emissions associated with the fossil fuel sector. And if it is blue hydrogen, well, we still need to consider the methane leak associated with blue hydrogen production. Now, combining these emission changes, what we see in the response of the methane concentration in the atmosphere is that if we leak little hydrogen in the atmosphere, basically we see just a linear response to the methane emission change. But as we increase the amount of hydrogen we lose to the atmosphere, the picture changes. And this because there is so much additional hydrogen in the atmosphere that the methane sink gets weaker. So even in the green hydrogen scenario, we see an increase in methane concentration regardless of the lower methane emissions. And clearly the thing becomes more drastic if we consider blue hydrogen with relatively high both hydrogen leakages and methane leakages. The interesting thing here is that, as I mentioned already, the soil sink is largely mitigating these impacts because basically when we emit hydrogen to the atmosphere, most of it is going to be absorbed by bacteria in the soil. And this is a very ubiquitous sink. Virtually all soils that have been investigated worldwide have been measured to uptake hydrogen. It was originally believed to be abiotic mediated, and around 10 years or so, 10 years ago, there was the first isolation of a high affinity hydrogen oxidizer. And since then, they found the capacity for bacteria to consume hydrogen in a lot of bacterial phyla. And our goal was, well, since in global climate models, currently the soil sink is represented very poorly, we wanted to improve this parameterization, develop an observation-based and hydroclimatic-driven mechanistic model. So what we did is we particularly explore how the hydroclimate is impacting the soil sink. And here is the crucial role of soil moisture. I'm representing here how the hydrogen uptake varies with a strong nonlinear behavior as a function of soil moisture. And this can easily be obtained starting from a mass balance of hydrogen in a soil root zone. And the interesting thing here is that if soil moisture is very low, there is biotic limitation, because what happens is that hydrogen can diffuse into the soil, but bacteria suffers water stress and do not actively consume hydrogen. Then if we increase the moisture, we have a maximum uptake. And as we go to even higher moisture, there is a diffusive limitation because hydrogen is not or very little soluble in water. And so there is no uptake. With this framework, we could reproduce observation data measuring the Harvard forest across a year, where we see this seasonal trend with the uptake being maximum in the summer and minimum in the winter due to low temperature, high moisture, and even snow cover, which basically introduces a diffusive barrier for hydrogen to diffuse into the soil. So using the parametrization, what we end up is a simulation basically that looks like this. Now, the parametrization has been included in the global climate model of the Geophysical Fluid Dynamics Laboratory at Princeton. And it's really an improvement compared to what we had before. And it shows clearly what are the limitations occurring across the world. You recognize the deserts, which are too dry for the uptake, or the tropical forests, which are too wet for a strong uptake. There are still challenges with this, clearly. In particular, the biotic parameters are not very well constrained, and I'm going to talk at the end about how we're developing a project to solve these issues. The last topic I want to mention is about ammonia. Ammonia as a convenient hydrogen carrier. So hydrogen itself is an energy carrier, so ammonia will be the carrier of the carrier. And my professor likes to say that ammonia is like a postdoc, and hydrogen is the professor getting the projects and then just giving it to his postdoc. So here I'm showing a scenario from the International Renewable Energy Agency that shows how in 2050 we might have a large international trade of hydrogen, in particular from renewable rich regions like North Africa, Middle East, Australia, to demand centers. We're talking about Japan, Korea, and even Europe. But transporting this hydrogen is very challenging, because while hydrogen has the highest gravimetric energy density of all fuels, it has also the lowest volumetric energy density. So we'll need a lot of volume to transport this hydrogen. And the potential solution, which are compressing hydrogen to very high pressure, or liquefying hydrogen to temperature that go at minus 250 Celsius, are very energetic demanding and prone to hydrogen leakages, which is problematic clearly in the first place for safety issues and fire hazards, but also for clearly hydrogen and direct greenhouse gas effect. So the industry is really thinking about converting this hydrogen through ammonia through the Haber-Bosch process. This is a very well-known industrial process, and then transporting ammonia instead of hydrogen. So an ammonia value chain would look more or less like this. We start from a primary energy input, convert it to hydrogen. We clearly have some energy penalty loss. Then ulteriorly converting it to ammonia. The conversion from hydrogen to ammonia is another 10% of energy penalty. And then ammonia could be cracked, meaning it could be split again into hydrogen and the atmospheric nitrogen, so that we use hydrogen. But this currently is a very energy intensive process, around 50% efficient. And so there is a lot of hype about the possibility of burning directly ammonia. And in particular, for example, Japan has a national strategy to use ammonia in coal plants for power generation. And so our concerns here are mostly dedicated to potential emissions of reactive nitrogen species. We're clearly going to have some leakages. This, for example, is an analysis that collaborator of mine did showing how the largest fertilizer production plant in the US, which is located in Louisiana and produces around 4 megatons of ammonia per year, is already leaking some ammonia. This is ammonia plume around it. And ammonia is problematic, well, because it's toxic, but also for air pollution, particulate matter formation, and water pollution after deposition. And then there are challenges with ammonia combustion because ammonia is not a great fuel and it can produce a lot of NOx as well as emitting unreactive ammonia. And really important for the climate change mitigation solution, N2O. N2O is one of the most powerful greenhouse gases. It's around 300 times more powerful than CO2. So taking some number, we did some global analysis to understand what an ammonia economy, how an ammonia economy could perturb the nitrogen cycle. For example, an ammonia economy of 30 exajoule per year, this is more or less equivalent to 5% of current global energy demand, would require a 10% increase, a tenfold increase in current ammonia production. And ammonia is already the most produced chemical worldwide. And if we introduce some leakage rate, we see that the perturbation could be relatively high. And our particular interest for, as I mentioned, we want to mitigate climate change are the potential emissions of N2O. So here I'm showing greenhouse gas footprint of electricity production from different energy sources. These brown values are from the IPCC. And I'm also accounting for green ammonia combustion and blue ammonia combustion. And I'm summing to the upstream emissions associated with ammonia production. For example, the methane emissions associated with blue hydrogen and then blue ammonia production. And I'm summing the impact of N2O with a leakage rate that goes from 0 to 1%. What we see is basically that clearly, if it is at 0%, ammonia could be a good fuel in terms of climate impact, but at 1%, it can become worse than coal. And so we discuss in the paper how really optimizing the ammonia energy economy will require best use pathways, practices, technologies, some of which are not yet developed, and regulations.
1 minute.
Perfect. Last slide. I want to just touch base on the projects I'm currently involved with. I'm co-supervising a PhD student at Princeton University that is assessing the hydrogen water footprint. Then I'm a collaborator in a project in collaboration with microbiologists at Princeton to better constrain really the parameters for the soil uptake, because we believe this is a crucial aspect in mitigating hydrogen emissions and being sure that is, for example, stable under climate change scenarios. And I'm also involved in a big project sponsored by the Department of Energy to better assess the various terms in the global hydrogen cycle. And I conclude by saying that hydrogen holds the greatest potential as a low carbon fuel for the future, but we need to address various challenges. I'm sure Luigi is going to talk after me about the challenges of green hydrogen production and the quest for new materials and the efficiency. My research is really on the environmental side, looking at sustainability of the production, leakage minimization, and optimization of ammonia management. And with these, I conclude. Thank you very much.
Thank you. We ask questions towards the end. We have first the 3 candidates, or we can proceed to ask questions right away.
Please proceed.
Okay. So a question that I will ask the 3 candidates is, can you already did a pretty good job. First of all, congratulations on your work. Very, very important. Can you tell us, let's say, what is your contribution in this work distinguished from the advisor's contribution? This is a question I will ask formally to all three candidates for.
Okay, well, I led the three papers I presented. I led the research, as in we planned it together with the supervisor, and then clearly I did all the research associated, so the development of the models and the software. My supervisor experience here is really in ecohydrology, and that's where we started. The connection was with the soil sink originally for hydrogen, exactly because the soil sink is the crucial term for hydrogen mitigation, and there is a huge hydrological component. I've also, I need to mention, and I didn't mention before, that for the other paper, especially for ammonia and the hydrogen feedback with methane, I've worked with great collaborators like Steve Pacella, Robert Sokolow, who really have a grasp on the energy sector scenarios, and Fabian Polo, who's a NOAA GFDL scientist, which can use the global climate model and was really useful in this sense for global analysis.
Thank you. I would like to open to also other members of the committee to ask questions at the judges.
Yeah, maybe I can follow up also with a generic question that continues with Guglielmo's. So what is really the big new thing generally in the field that your work contributed to?
Regarding hydrogen and methane, which I think is really something overwhelmingly important and little recognized by the community, my contribution is really has been to provide an analysis that could give different scenarios of hydrogen displacement of fossil fuels, because we knew already the physical mechanism in the atmospheric chemistry, but we had no integration with the sort of energy sector. Regarding the soil sink, basically, my model is the first hydroclimatic-driven parameterization that there is, just because hydrogen has not received a great deal of attention, and now clearly it is because of the global hype there is about it. And ammonia, this is really something at the research level, so even the consideration about reacting nitrogen emissions, I think we are sort of the first one to do it.
Thank you.
Thank you. I have maybe a couple of quick questions, or maybe general, these are very general curiosities, at least for me. So I definitely see the potential, you know, as a background, I started as an aerospace engineer, so, you know, I definitely resonate with when you say that hydrogen is extremely, let's say, efficient once you burn it. The only thing is that you need to carry a lot of volume with it. So from which, you know, why it is liquefied in rockets and other things. The other thing is that I understood the idea that you mentioned, that hydrogen doesn't dissolve in water really well. Now, this is just a general question. So living in North Carolina, where the soil is mostly clay, and there is a lot of clay in all of America at the end of the day, the reddish dirt, quote unquote, that we see in many towns. Clay, when it's oversaturated, tends not to absorb, basically to if I understood it correctly, you know, becomes impermeable in a way. So what you're saying, it's related also to this, right? That
yeah, that's perfectly correct. Like when clay, which has usually clay is where it rains a lot, it's humid enough for the soil to have become clay. It becomes almost impermeable, and particularly to gas diffusion in the air-soil phase. So bacteria in those conditions do not consume hydrogen. And it's interesting that we know there is a diffusive limitation because we have shown it with easy math. But also from lab experiments that we're doing, it seems that also these bacteria, even if they had some hydrogen available at those high moisture level, probably would not consume it. And we're not sure about the reason why. It could be an anoxic environment development, but this is still an open question.
Okay. It's okay for me, but there may be additional questions from Natalie or from other participant. I think that if, you know, maybe we have a time for a quick question until we move to the next.
Yeah, I just maybe had a quick, maybe I looked at the map. I really liked the map that you showed. And it seemed like in Spain, you have more H2 uptake than in other European countries. Was I correct?
Yeah. So because basically, let me replay this. Oh. Okay, it doesn't replay, I'm sorry. But anyway, because in very dry regions, in deserts, the uptake is biotic limited. In forest and humid regions, it's diffusive limited. It seems that the optimal situation for hydrogen to diffuse into the soil and be consumed is in semi-arid environment that have enough water for bacteria to be active, but also not enough for hydrogen to stop diffusion through the soil. And that's why some semi-arid region show higher uptake.
Thank you, interesting.
Okay. If there are no additional questions, we can thank Matteo for your presentation, and we can move on to the next presenter.
Okay, good morning. I will try to share my screen. Okay, I'm not sure if you can see it.
Yeah.
Okay. Can you see the presenter view or the full screen now?
We see the presenter view.
Oh, okay.
Maybe
so...
there is a trick to flip it.
How about now?
Perfect.
Okay, great. Yeah, so thank you very much for inviting me to present my work today. The title of my presentation is Catalysts and Electrodes for Affordable Hydrogen Generation and Utilization. I'm Luigi Osmieri, and I'm a staff scientist at the Los Alamos National Laboratory. So I would like to start with giving motivation of my research and explain a little bit why my work is relevant and important. So as Matteo also presented described in his presentation, so we have like the big driving force for this research is the issues caused by the global warming, with many detrimental effects evident every day more all over the world. For mitigate, reduce these effects, ultimately we need to reduce the carbon dioxide emissions in the atmosphere, which are generated and caused primarily by the energy production. So the United States Department of Energy has implemented the so-called Hydrogen at Scale initiative, basically trying to find paths for integrating hydrogen across different applications and sectors in our economy in an increased interconnected way. So this will help to decarbonize various sectors, and it will also boost the economic growth and the creation of new jobs. As we can see from this plot, in the over the last decade, the fraction of electricity generated in the United States with the renewable sources has been increasing, and this is an opportunity, but is also a challenge because the renewable sources like solar and wind, for example, are intermittent, and do not necessarily match the electricity consumption peaks. So there is a need of storage the electricity produced using these renewable sources. One of the ways is to use electrochemical energy conversion devices. More specifically, we can produce green hydrogen from water electrolysis using electrolyzers, and then storing the hydrogen that is produced and then use it back to produce electricity in using fuel cells. So my research is focused in low temperature systems. So these systems operate below 100 degrees C and at a few bar of pressure, which has the advantage of enabling fast startup and shutdown. But due to these mild operating conditions, there is a need of catalysts to enhance the reactions, the electrochemical reactions at the electrodes. Unfortunately, the most effective catalyst for all of the electrochemical reactions involved in these devices, in water electrolyzers and fuel cells, are based on platinum group metals, or noble metals, if you prefer, which are, as you can see, the best catalyst for the reaction involved in fuel cells, so the hydrogen oxidation and the oxygen reduction, in particular platinum in this case, while for the reactions involved in the water electrolyzer, so the hydrogen evolution, the best catalyst is the platinum, and for the oxygen evolution, the best catalyst is the iridium. These noble metals range are located in the top of the so-called volcano plot because they have that very nice intermediate binding energy with both the oxygen and the hydrogen molecules, and so they can provide the very efficient electrocatalysis. As shown in this plot that shows the variation of the price of the platinum group metals over the last 20 years, we can see that this price undergoes big fluctuations. And currently, for example, iridium is priced at $4,700 per ounce. So this is creates, of course, big challenges for the implementation of these electrochemical energy conversion devices on the large scale. Specifically, these plots showed like the cost breakdown analysis for proton exchange membrane fuel cells and electrolyzers, where we can see when we we do the scale up of the manufacturing, the fraction of the cost of the device that is attributable to the catalyst becomes larger and larger. The other drawback of these materials, of these PGM materials, is that they are mined in a very few locations around the world. In particular, South Africa and Russia are the primary producers. And so this creates a challenge for importing these materials from these countries. So replacing the platinum group metals with catalysts made of earth-abundant elements will be very helpful to reduce the cost of the fuel cells and water electrolyzers, but also to reduce the dependence on the import from these sensitive countries. I would like to start to describe a little bit my work, starting with my work on the development and testing of PGM-free catalysts for oxygen reduction reactions, so with the application on the cathode of proton exchange membrane fuel cells as a replacement for platinum. So these materials are carbon-based materials which are doped with the nitrogen and transition metals like iron, cobalt, or manganese, and are synthesized after a heat treatment at high temperature. They present substantial differences compared to platinum catalysts, in particular for the nature of the active sites, the morphology, the interaction with the electrolyte that is also present in the electrode in form of the ionomer, and consequently on the structure of the catalyst layer. So there is a need to better understand the electrode structure property relationship to improve the performance of these materials in comparison with the platinum. So during my the initial part of my postdoc at the National Renewable Energy Lab, I focused on determining the oxygen reduction kinetics on iron nitrogen carbon catalyst in an operating fuel cell electrode. Specifically, we proposed a modification of the kinetic equation to include two experimentally measured parameters, which are the iron oxidation state variation and the redox potential at which this variation happens. By inserting these terms in the overall kinetic equation, we were able to fit with a very good agreement a broad range of experimental data collected at various operating conditions in terms of temperature, pressure, and in a broad range of potentials. So we have validated our model, which was later applied in another work in order to quantify the improvements that are needed to meet the performance target goals, and also identify what are the possible improvement strategies. So starting from our initial baseline experimental data, we showed how much improvement is needed in terms of both the catalyst activity, so in the material side, but also in terms of electrode structure design, so in terms of integration of these catalysts in a electrode. So this work provided the guidance for catalyst development and electrode engineering to quantify these improvements that are needed to meet the targets. Talking about electrode engineering more in detail, when we fabricate the electrode, we basically mix the catalyst powder with some ionomer and we disperse it into a solvent, forming an ink that gets deposited on various substrates in order to fabricate the electrode. So we have explored different fabrication parameters like the ionomer content, the ink solvent composition, and the ionomer equivalent weight, and found a big variation of performance depending on the operating condition. So we tried to develop a strategy to understand why these improvements were actually happening. I developed two methods to quantify the mass transport resistance in these PGM-free electrodes based on the limiting current measurements, one based on hydrogen oxidation limiting current that does not consider the generation of water, and another method a little bit more complex based on hydrogen reduction reaction limiting current, oxygen reaction limiting current, which considers the generation of the water within the electrode. Overall, we applied these methods to several different fabrication methods and operating conditions, and we basically provided a systematic approach for understanding the impact of electrode fabrication variables to improve the performance, showing that the best performing electrodes in different operating conditions are the ones that minimize the ohmic proton transport resistance in the electrode and the bulk gas oxygen gas transport resistance. Another very important aspect is the durability of these materials, which is challenging compared to the standard platinum catalyst. So I investigated several different accelerated stress tests in different conditions for these catalysts, and demonstrated a trend that correlates the higher degradation that happens when the cathode is operated in presence of oxygen, so when the ORR actually takes place, rather than in an inert atmosphere. And this degradation correlates well with the loss of iron sites, the oxidation of the catalyst surface, and the decrease of the cathode kinetics. So these findings were then used later for developing, validate, and disseminate the testing protocols that are now recommended by the US Department of Energy for testing and assessing performance and durability of PGM-free catalysts for PEM fuel cells. I would like to talk a little bit now about my work on the other electrochemical conversion device that I talked about, which are the water electrolyzers for generating hydrogen. So currently, the two widely used technologies for generating hydrogen at low temperature are the liquid alkaline electrolyzer, which can operate with a PGM-free catalyst, but has the drawback of using highly concentrated alkaline solutions and operating at low current densities. On the other hand, the second technology is the PEM water electrolyzer, or proton exchange membrane electrolyzer, which can operate in pure water and at very high current densities, but can only operate with the PGM catalyst due to the highly acidic conditions in the electrodes. Currently, the development of more efficient and performing hydroxide exchange membranes, we can actually rely on a new technology, which is the anion exchange membrane water electrolyzer, which can combine potentially the two advantages of the previous system, so the use of a pure water and the use of PGM-free catalysts. However, this technology is new and requires understanding of catalyst design, electrode fabrication, and durability. The main challenge when we are talking about the oxygen evolution reaction, so the anode of this anion exchange membrane electrolyzer, is that we cannot use high surface area and conductive carbon materials because these will undergo oxidation. Also, we can only rely on transition metal oxides, which typically have a low surface area. So considering that the nickel iron oxide hydroxide are the most active OER catalysts in alkaline media, I tried to develop a method to increase the surface area and basically obtain a more active catalyst. This method is based on aerogel synthesis. So the aerogel basically method enables to remove the solvent and create like a gel-like morphology in a solid material. So we obtain a very high surface area nickel iron oxide with more than 400 square meter per gram surface area, which if underwent to different heat treatments at different temperatures, show that the heat treating at a low temperature like 150 degrees C show the best oxygen evolution reaction activity. After testing in a water electrolyzer and characterizing the material before and after the test, we noticed that this aerogel heat treated at low temperature showed a disordered structure with randomly oriented small crystalloids of the size of about 2 nanometers, which after testing changed their morphology to form a needle-like crystals, while the catalysts that have a low activity, like commercial materials or catalysts treated at high temperature, show larger crystalloids that do not undergo structural modification after testing. And so we have elucidated how the impact of the catalyst morphology and structure induced by heat treatment, for example, can improve the performance on application of this catalyst in a real water electrolyzer device. We also investigated the break-in of these materials in an electrode, showing that the good performing catalyst actually shows a continuous activation over up to 10 polarization curve measurements, showing also the color change from greenish yellowish to black, while the low performing catalyst started to degrade right after the first polarization curve measurement and did not show the same color change. Finally, comparing our results with the one of a state-of-the-art proton exchange membrane electrolyzer that uses iridium oxide as the catalyst at the anode, we showed that we were able to get very close when we operated the electrolyzer with a low concentration of KOH solution of 0.1 molar, which is way lower than the higher than 4 molar used in the liquid alkaline electrolyzers. However, the performance in the pure water is still lower and requires more investigation due to the challenges in the transport of the OH ions within the catalyst layer, which in presence of DI water only relies on the interface between the catalyst and ionomer. Finally, to conclude, my future work is currently based on continued development of PGM-free catalysts for oxygen reduction and oxygen evolution, with the aim of improving performance and durability. And I also recently started to expand my research on other reactions like hydrogen evolution and CO2 reduction reaction. It is important to continue to better understand the integration of this material into electrodes of the real operating device to improve the performance. This could help the efforts of creating a possible future where our energy system will be based on hydrogen. Finally, I would like to thank all of the institutions where I carried out my research and the funding agency, in particular the US Department of Energy through the ElectroCat Consortium, and also the Los Alamos National Lab LDRD program for my director's postdoctoral fellowship. And I would also like to thank all of you for your attention. I will be happy to answer any questions. Thank you very much.
Thank you for the very nice presentation. Thank you. I'm going to start with the classic question. You already elucidated much of what I'm about to ask. That is your personal contribution in these projects, also in the broader context of advisors, collaborators.
Yeah, so for the topic of the hydrogen generation, so really my contribution was to develop this aerogel synthesis method and apply it as, so applying these aerogel materials as oxygen evolution reaction catalyst and integrating them into an electrode. So this is like a new work that we are actually recently submitted to a journal for publication. So basically the biggest contribution that I gave this is in this area is this, like, okay, let's try to apply these materials as a catalyst, which has not been done before. And in the context of the project in which I work was innovative. And also I try to create the connection with the partners, like, for example, Argonne National Lab and Oak Ridge National Lab, which have very advanced characterization techniques. I try to establish the connection with these labs and try, okay, help me to understand what happens in this catalyst during testing and after testing, and understanding why some of them perform better than others in the device. Talking about the other part, so the oxygen reduction reaction catalyst for fuel cells, I think the biggest contribution that I gave is like trying to understand why these electrodes perform in this way when we change the fabrication method and we change the ink formulation parameters. This has been done a lot for standard platinum catalysts in the past, but there wasn't almost anything done for PGM-free catalysts. So I think I published like 5 papers in this area, and hopefully I helped other people working in this area to understand something more and build their research on my preliminary works, let's say.
Thank you. Natalie?
Yes, possibly a specific question. So why in the hydro or aerogels do the lower temperature and yield gels perform better than the higher temperature and yield ones?
Yes, so what we have basically found is that when when we heat treated at this low temperature, the modification compared to the original aerogel without any heat treatment is basically minimal, or at this low temperature, we basically just desorb some moisture that was absorbed on the original aerogel. We did not really modify the structure. And while heat treating at very high temperature, we create these like rock salt crystals, which have the structure of a nickel oxide. So when we test and we applied the high potential of the anode of the electrolyzer, this disorder structure or random orientation small crystals have the ability of like basically modify and creating this like lamellar structure, which we attribute to be iron doped nickel oxyhydroxide, which is the highly active phase for oxygen evolution reaction. On the other hand, these larger crystals of the commercial materials or catalysts heat treated at high temperature do not have that ability. They stay in the same form, and so they have a certain oxygen evolution reaction activity, but not that high, and they cannot basically take advantage of the random iron doping inside this nickel hydroxide, into the original nickel hydroxide structure. We have more advanced data coming from Mossbauer and X-ray absorption spectroscopy, which I didn't have time to talk about in this short presentation, but we have a very nice story that basically points towards like the ability of these small crystals to undergo easily this modification, unlike the larger ones.
Thank you.
Additional questions from the, thank you. Additional questions from the audience? So if not, we can move to the next candidate. Thank you so much for the very, very exciting work. Thank you.
Yeah, thank you very much.
Thank you.
Thanks. Trying to see if I can stop sharing. There you go.
Can you see the screen?
Yes, but yeah, now it's good.
Yeah. Good morning, everyone. For me, it's an honor to be shortlisted also this year for the award. And I'm going to present some work that we recently started on achieving net zero energy emissions in agriculture. My slide does not change. I don't know why. Sorry. Okay. So why focusing on agriculture? So agriculture is the most impactful human activity. 90% of water use, 5% of energy use, 15% of global greenhouse gas emissions, and many other impacts are from agriculture. And this is only if we consider agriculture. If we talk about food systems, the share of energy use and greenhouse gas emission is way larger. And if we make agriculture more sustainable, we can solve many of our challenges, including food and energy security, climate change, biodiversity loss and pollution, and also land and water scarcity. In addition to these big impacts from agriculture, we have also a challenge, and the challenge is that by 2050, population growth and changes in diets are expected to increase global food demand by 50%. So in other words, in the next 30 years, we will need to produce the same amount of food as we did cumulatively over the last 8,000 years. So this is a huge challenge. And therefore, satisfying the global demand for food without causing additional climate change and environmental degradation is, in my opinion, the central challenge of the 21st century. And in my lab, indeed, we focus on solutions to improve agricultural sustainability. And today I'm going to focus on the work we are doing on net zero energy emissions in agriculture. And as you can see in the lab, I have also several young Italian scientists that are mainly working indeed on sustainable energy research topics. And I'm going to show some of the results of this research we've been doing in the past 2 years. And in this figure, we see the emissions from agriculture, which are about 7 gigaton or 15% of global greenhouse gas emissions. And they come from on-farm energy use, synthetic nitrogen fertilizers, rice cultivation, enteric fermentation, which is from livestock, manure management, and crop residues. And in this presentation, I will focus on some of these sectors and the work we've been doing on how to achieve net zero emission, with a special focus on energy. And I would like to start with synthetic fertilizers. So synthetic fertilizers are produced from the Haber-Bosch process, which is the building block to produce ammonia, that then is used to produce fertilizers. However, the Haber-Bosch process today relies on fossil fuels, mainly natural gas and coal, uses 2% of global energy, but is also very important because about half of the global population, or 3.8 billion people today, are alive thanks to the Haber-Bosch process. So without the Haber-Bosch process, half of the global population will not be alive. And the reliance on fossil fuels of the Haber-Bosch process commits humanity to emission levels that are not compatible with climate goals. At the same time, the reliance on fossil fuels expose food systems to energy imports and therefore energy and supply shocks. And this research indeed started last year when Russia invaded Ukraine, and we had a spike in natural gas prices, which also created a spike in fertilizers price. And as you can see, there are about 80 large ammonia production facilities worldwide, and they are mainly in developed countries. And the question was, how can we reduce reliance on natural gas? What are the pathways we have to produce net zero ammonia without natural gas? What are the environmental impacts? And what are the food and energy security implications? And this project started from a gift from the ClimateWorks Foundation last year. And we analyze first the vulnerability to supply shocks of food production reliance on Haber-Bosch ammonia. And in panel A, in the top, we see in green countries that are net exporters of ammonia. So these are countries that have a chemical industry and they produce ammonia and they export ammonia. For example, Germany is an exporter of ammonia. However, when you account for the reliance of these countries on fossil fuels, countries like Germany become net importers, so they become orange or red in the figure. So with this analysis, we show the reliance of countries on fossil fuels, and we also show that only few countries, the countries in green in the panel in the bottom, are the countries that are not relying on any imports. And therefore, only a few countries control the energy resources that are required to produce fertilizers. And we also quantify the people that are reliant on imports of either ammonia or natural gas that is used to produce ammonia. And we find that about 1.8 billion people, or 20% of the global population, is indeed reliance on this supply shock. And then we use process engineering and energy engineering to study the current production method of ammonia, which we call business as usual. So in the current production method, we have coal or natural gas. Coal is mainly used in China. We then use steam methane reforming of natural gas or coal gasification to produce hydrogen, which is the most energy and carbon intensive process. Hydrogen then is purified by removing CO2, and hydrogen is then combined with pure nitrogen from the air that is produced from an air separation unit, and at tight pressure and energy is produced through the Haber-Bosch process. We produce ammonia. And very importantly, hydrogen production is the most energy and carbon intensive process of this production of ammonia with Haber-Bosch, and uses about 98% of the energy in the process. We also accounted in the study for natural gas leaks that are very important and account for about 1.5% of the natural gas used. And as I mentioned, the air separation unit is very efficient and uses only 1 or 2% of the energy used by the whole process. We then quantified the emissions of in each country based on production, and we can see that the emissions depends on production of ammonia, but also the ways of producing ammonia. For example, China is a big producer, but is also relying for 80% on coal to produce ammonia, and therefore this is why China has such huge emissions. And globally, ammonia production for fertilizers emits about 390 million tons. We then studied routes to produce net zero ammonia from Haber-Bosch process. And the routes consist in carbon capture and storage, electrification with low carbon hydrogen, and biomass. The carbon capture and storage route relies on retrofitting with CO2 capture unit the current business as usual process. And here CO2 is captured. We can achieve a capture efficiency of about 95%. The residual emissions that are about 5% need to be offset with negative emission technologies such as direct air capture. And in the study we model direct air capture as a solution to achieve net zero and offset indeed these residual emissions. The other approach is electrification, where instead of using fossil fuels to produce hydrogen, we use water electrolysis powered by low carbon electricity. And very importantly, also this process is not net zero, because solar, wind, nuclear or other low carbon energy technologies have a carbon intensity. For example, solar has a very large carbon intensity. This is the median value, and these in the parentheses are the minimum and maximum value from a life cycle assessment. And so also here we have residual emissions, and to achieve net zero emission, we model how for example, direct air capture can help to achieve net zero, and what are the implications of using direct air capture. And then the other route is to use biomass. So instead of using fossil fuels, we have biomass, we do gasification of biomass, and we produce hydrogen and then ammonia through the Haber-Bosch process. And also here in the supply chain, we have some emissions that have to be offset to achieve net zero ammonia production. And in this study, in this figure, I show the summary of the results in terms of energy, land, and water intensity of the free decarbonization routes to produce net zero ammonia from the Haber-Bosch process. And as you can see, all the processes are more energy intensive than the business as usual route. In particular, the electrification route is 25 times more energy intensive than the business as usual route, because here we need energy, in particular electricity, to produce hydrogen and also to run the process. While from carbon capture and storage and biomass, we have biomass or fossil fuels that have embedded energy and hydrogen molecules that can be used as a feedstock to produce hydrogen. And also in terms of water and land intensity, we see that the free net zero routes are more energy and water intensive. In particular, biomass because it uses a lot of land to grow biomass through the photosynthesis process. And very importantly, these scalar logarithms. So we are talking about orders of magnitude larger in terms of energy, land, and water use with these three net zero routes. And then we study also the land and water scarcity that can be created by low carbon hydrogen production. And in this map, we show in orange and red the countries that will have land scarcity or water scarcity if large-scale electrolytic hydrogen production were to be produced in a net zero economy. And basically this analysis shows that some countries will be constrained by domestic natural resources and will not be able to achieve self-sufficiency in electrolytic hydrogen production, implying that some countries will have to rely on imports of hydrogen because they don't have enough natural resources to produce low carbon hydrogen. And what are the implications on achieving net zero ammonia production through the Haber-Bosch? So first, we show that electrolytic hydrogen production and biomass routes eliminate the use of fossil fuels. So we don't rely anymore on imports of natural gas. However, these processes, they are capital intensive and they have a very slow commercialization. In fact, today only 0.01% of global ammonia is low carbon, and this is about 0.02 million tons per year. And by 2030, there are projects in pipeline that commit to the production of about 15 million tons of low carbon ammonia. So very slow progress in this direction. And we also show that there are environmental trade-offs in terms of energy, land, water use, but also biomass use. And these can further exacerbate land and water scarcity, which are already a big issue that we have today. And therefore, net zero routes need to be combined with local resources available. Importantly, even if we produce net zero ammonia with the three routes that I shown from the Haber-Bosch, these will still commit to rely on large facilities, which are about 80, and this will therefore imply that countries like African countries or like in the global south will still rely on supply chain to import ammonia from other countries. And therefore, in the current work building on this, we are exploring alternative processes to the Haber-Bosch process to produce ammonia. And these processes are called distributed ammonia fertilizers production technologies, and are, for example, electrochemical synthesis and plasma activated processes. So in these processes, we have solar and wind power that can produce on-farm nitrogen fertilizers, so we can produce on-farm ammonia, and therefore they can drive the chemical reaction of ammonia production at a small scale, at a local scale, instead of having large facilities at high pressure and temperature. These technologies are still in development, so we are partnering with the Stanford Hydrogen Initiative. We just got a seed grant, and we are studying how these technologies can compete. They can create a cost competitiveness compared to net zero Haber-Bosch process to produce ammonia fertilizers. And going back to the figure that I've shown you at the beginning, so far I focus on synthetic nitrogen fertilizers. There are other important components in terms of emissions from agriculture, and two of these are crop residues and livestock manure, which together emit about 1.5 gigaton. And we're doing some work on studying how crop residues and livestock manure can become a solution from being a problem. So today they emit 1.5 gigaton, and we are studying how processes like anaerobic digestion can help to achieve net zero emission and reduce environmental impacts. For example, we are studying how much biogas which is biomethane or bioenergy, can be produced from livestock manure and the crop residues. We are doing this at the global level using geospatial analysis on biomass availability. And we are also studying how we can produce fertilizers from the digestate, so the liquid part of the anaerobic digester from livestock manure and crop residues. And lastly, we are also studying the on-farm energy use component. So we are looking on how to achieve net zero energy emissions on farm. And in particular, we are studying irrigation water pumping. So here you see the geospatial distribution of irrigated areas worldwide, and you see the energy use, which we account. And then we are also considering different water sources. So if you have groundwater pumping, you use more water than if you have surface water pumping, because you indeed have more energy to pump from deep underground. We are also studying different technologies for pumping water, in particular diesel pumping and electricity pumping, and different irrigation efficiency technologies like drip irrigation, sprinkler irrigation, and surface irrigation. And we are studying these in the context of net zero pathways. So we are studying how introducing low carbon energy such as solar, wind, and nuclear can help to achieve net zero emissions, and what are also the impacts of these low carbon irrigation systems on energy systems, in particular electricity systems. And with this, I thank you very much for your time, and it is an honor for me to present, and I'm looking forward to meet all of you in Washington, D.C. in 3 weeks. Thank you.
Thank you. Thank you. So let's go to the right ritual question of if you can outline your contributions versus collaborators.
Yes. So this work was done when I started my position here as a principal investigator. So at the beginning, obviously, I was building the lab, so I was alone. So the first studies that I shown have been done by me mainly. Indeed, I'm the first author. And at the time, I had a visiting scientist from ETH Zurich, which the name is Paolo Gabrielli. And together we were working on net zero chemical industry. So as you see the connection, the chemical industry as ammonia, plastics, and methanol, we were working on that, and then we translated the ammonia to fertilizers. So it was a spin-off idea from the work we were doing together on the chemical industry, and then we applied to agriculture. And starting from that work, that was funded also by ClimateWorks and is having a lot of attention, we basically went in the direction on net zero energy emissions in agriculture, because we noticed that no one really focused on net zero emissions in agriculture. So a lot of work has been done on net zero energy systems in the past 8-10 years. Then recently there has been work on steel, cement, chemical industry. There is a lot of work on hydrogen, ammonia. As you've seen, everyone is working on hydrogen, ammonia, but very few people have focused so far on agriculture, especially the energy part in agriculture. And so we decided to go in this direction that is very novel and is having also a very important impact, because as I've shown, agriculture alone, without considering food systems, is 5% of energy use and 15% of greenhouse gas emissions. If you consider food systems, so you transport, packaging of food, conservation, we reach about 30% of greenhouse gas emissions and 30% of energy use. So it's this very large sector that deserve investigation, because to achieve net zero emissions and meet climate goals, we don't need only to focus on electrification of energy systems, but we also need to focus on agriculture. And for us, agriculture was the elephant in the room, and it was a kind of natural to go in that direction, because I've been working on agriculture since my my PhD.
Thank you.
Yeah.
Yes, so there were a lot of ideas usually to get like new types of solar cell technologies into greenhouses, but often people had trouble actually to get that funded. Does that make sense to you, to integrate energy harvesting systems into greenhouses to at least lower to a certain extent the energy consumption, if it's now for heating or cooling, depending where you are? Or would that just be a drop of water on a hot stone?
Yeah, I can give you an example. So for example, for fertilizers, so as I mentioned, fertilizers today are producing about 80 large, very large facilities in the world. And so you need a big chemical industry, you need the know-how, cannot be done everywhere. And there are these distributed ammonia production technologies that they have low technology readiness level, but they actually have a huge potential, and they are gaining a lot of attention. So because you need a container scale, you can apply it in your farm, no? And is moving very quick in this direction, the research, but also the implementation. So, for example, with this project, we are partnering with a startup that indeed produce ammonia from electrocatalysis. So you have solar and wind, which are technologies we have, mainly solar, that is going to be very cost competitive to produce energy. And then you need this new way to produce ammonia that basically does not rely on high pressure and has lower temperature compared to the other options. So you don't need economies of scale. You can have a small facility and you can then apply it everywhere. So it's very small, modular, and so also the learning curve is going to be very quick and is going down very quick, like was for solar in the past 20, 30 years. And the same is for irrigation. So irrigation historically has been done with diesel pumping. Okay, and now the next step, also the UN recommend to use solar power drip irrigation. So you have on farm, you have your solar panels, and you have drip irrigation, which basically is you just give droplets of water where you need it, when you need it, in where there is the root of the trees. So it's super efficient and also reliant on electricity. And these processes as well, they have the advantage of being small and modular. So it's called the soft path approach compared to the old hard path approach. So large, centralized, reliance on fossil fuels that then obviously has a lot of issues like import dependency, supply and energy shocks. And the same is with anaerobic digestion. So anaerobic digestion is huge in Europe, also in Italy. So there are more than 20,000 facilities, and these are small modular. So you have your farm, you have your 200 cows, 1,000 cows, you collect the manure, and you produce locally with an anaerobic digester, biogas, and you can use that energy from biogas to run the farm. So you can produce heat, electricity, to produce cheese, to cool down the farm, to heat the farm. And so they have huge potential. But on the other hand, there are trade-offs. For example, in the US, this technology is not very widespread because of low natural gas prices. So it's not cost competitive yet here. But in countries like Europe, was, and especially after what happened last year, is growing exponentially, I can say, in the past year, this other technology. So they have the advantage that they are low carbon, small and modular, compared to the old hard path that is large scale reliance on fossil fuels and import and supply shocks reliance.
Thank you.
Yeah.
Thank you. Thank you for a very nice presentation. I don't know if there are additional questions from the audience. So if not, wait maybe just a few more seconds, but if not, I would like to introduce the sponsor of the award, the general sponsor of the award, that is going to address us with a few words. I want to introduce Professor Mario Strazzabosco. He's the director and clinical program leader of the Meadow Liver Cancer Program at Yale University. He's an internationally recognized expert in the care of patients with liver cancer. He has previously served as medical director of hepatology at Yale and is the former founding chief of the section of digestive diseases, chair of the Department of Surgery and Translational Medicine, and vice president of the School of Medicine at the University of Milan in Italy. Professor Strazzabosco, please, the floor is yours.
Thank you. You were talking probably of another person. Thank you for your introduction. Yes, it's always a great pleasure to hear the great work that has been done by our scientists, Italian scientists here in the US. And I have to say that my dad would be very pleased to see what is going on. He was a PhD in engineering. He worked on what was at the time considered a better energy, which is methane. And he clearly would be extremely pleased, as I am. As I understand your difficulty as a jury to adjudicate this hour to one or the other. And so thank you for your involvement with this, and congratulations to all the presenter, and good luck. Thank you.
Thank you very much. We see that also the connection with the candidates of this year. So very nice. Enrica, maybe yes, I wanted to pass the, I don't know if Alberto is still connected. No, but Alberto was mentioning to me he would have very much liked to give a big thank to Simona for all the work done in the organization. He forgot to mention at the beginning. Now, Eric, I pass the floor, the control to you.
Thank you very much. This has been a most interesting symposium, and thank you to you, the jury, and congratulations to the finalists. I see that Cinzia Zuffada, the president of ISNAF, is here, and I would like to ask her to say a few words.
Thank you, Enrica. Thank you, everyone. It has been a great event. I arrived late. I'm sorry I was on travel today, but so I could get most of the last two presentations. I enjoyed this topic very much. It's good to see two candidates from the past edition being here again. So it's a strong body of finalists here. It's great to see. It's very nice to see Mario as well. We are very grateful to the family. The Strazzabosco Award is our second oldest award after the Campese Award. It was established soon afterwards. So we are immensely grateful to the family for the support of ISNAF throughout the years. With that, I thank you all. Congratulations to the speakers. Bye.
Thank you, Cinzia. Bye-bye.
Bye-bye.
Right. Thank you.